Hi everybody, in this video we're going to learn how to take the derivative of the function e to the x. Now just realize that this x up here might not just be a variable x, it might be some function up here like e to the sine of x or e to the 5 of x, and it's going to involve our friend the chain rule. Chain rule is going to apply all the time from now on. So just realize this is video number 11, so in your notebooks title it appropriately so you can find it later on. To introduce the idea of what the derivative of e to the x is, I want to go back and just talk about x squared and its derivative. So what I'm going to do is go to the calculator here and grab your calculator and do this with me here just to practice the keystrokes. Let's have our calculator graph x squared, which we obviously know is going to be a parabola. And by now, with the power rule, we know how to do the derivative of this, but let's make our calculator do the work. And let's go to option 8 here, and let's have it graph the derivative. So let's pretend we don't know what the derivative is, or we just don't feel like taking it. Let's make our calculator do the derivative with respect to x of x squared. Now, another thing I want you to get used to, it's very easy to type x squared in, but we might be getting functions that are way more complicated, and rather than having to type in the function, you can just type in y1. Now, the way to get y1, if you forgot, is to do alpha trace. And y1 should pop up right there. Hit enter. And to get the calculator to graph the derivative of y1 for every x, I'm going to say the derivative when x equals x. All right, so now I'm going to hit graph. Here's my first function. There's the original x squared. And here is its derivative, which using the power rule, we know it's going to be 2x, and that is 2x. So we already could predict that. That's not a shocker to us, but this is going to be a lead into what we're doing with e to the x. So let's go to our notes here and label this in your notebooks. Notice that the second function, f2, gives the derivative of the original for any x value. Notice that when my original blue function, in this case, is at a minimum, the derivative is at 0. Notice that whenever my function is decreasing, the derivative is negative, it's below the x-axis. And whenever my original function is increasing, the derivative, the purple one or pink one, is positive. It's above the x-axis. These are things we're going to start to notice more and more. So now let's do the same thing. So make sure you get that copied down in your notes. Pause if necessary. Let's do the same thing with e to the x. Now we're really going to have to use the trick that we did here because we really don't know what the derivative of e to the x is. We're about to find out. So let's do second ln to get e to the x. And again, because we don't know what the derivative is, let's do math 8. So calculator, why don't you graph for us the derivative of y1? So on your calculator, do this with me. The more comfortable you get with these keystrokes, the faster you will be. So we're going to do the derivative, and let's see what happens. Now, I want you to watch very carefully. Keep your eyes glued to the screen here or to your calculator screen. Here's the original. Oh my gosh, look at that. It is the exact same thing. It's right on top of it. Nothing has changed. So this is very special. E to the x is the only function in the world where the original function is the exact same as the derivative. No other function in the world is like that. So e to the x is very unique in that way. So when you draw in your notebook, you can just do a different color or a dotted line right next to it to indicate that e to the x and the derivative of e to the x are the same exact thing. It's the only function where f of x equals f prime of x. No other function will do that. Okay, so this is key here. The rate of change of the function is the same as the function. So this is a quick way of writing it. The derivative of e to the x is e to the x. So you want to put a bunch of stars around this. This is huge. But again, this might not just be a plain old x up here. It might be another function. So we're going to use that chain rule. Chain rule never goes away now, even though you might wish it would. So this is the official rule here, using the chain rule. So if I have e to some function, notice the outer candy is blue, the inner gum is pink. The derivative, f prime, the instantaneous rate of change, will be the derivative of the outside. Well, the derivative of e to some function is itself e to that function, times the derivative of the inside, which is this pink one here, which we're going to write as f prime, whatever f may be. So again, the derivative of e to some function is that same thing, e to that function, times that chain rule. Okay, so make sure you write this down very carefully. If you have colors, it might help to keep it organized. And I'm going to show you some examples here. I have 3 examples. So pause the video if you need to. I'm going to move on. Okay, and let's not forget, I'm going to write this here just so you remember, the derivative of e to the x is e to the x. We're going to refer to that for every single example. So first one, I have e to this function here, a polynomial, 4x cubed plus 7x. So we definitely need chain rule because this exponent is not just an x. So we're going to do derivative of the outside. We're going to do the candy first. You can't get to the gum until you do the candy. So derivative of e to some function is itself e to some function. Nothing is changing. Times, chain rule in action here. I'll use parentheses just to make it clearer. Now that the candy's gone, I can get to the gum on the inside. So I have 4x cubed plus 7x. I need the derivative of that. Well, use the power rule. 3 comes down. I have 12x squared. Derivative of 7x is 7. So that one wasn't too bad. Just remember that this here is the gum on the inside, and this here was the candy on the outside. You do the outside first before you work your way in. All right, this one's a little bit more interesting here. I want the derivative at a certain value here for this function. Oh, this is getting interesting now. 3 layers, e to the sine of 7x squared. So I have my wrapper here, the candy wrapper, e to the whole function. Then I have the candy, which is sine. Then I have the gum on the inside, 7x squared. You cannot touch 7x squared till the very, very end. Before we even worry about evaluating it, let's just find g prime just with x, okay? So I'm going to do the derivative of the outside. Well, the derivative of e is just e, so nothing is changing. Times the next layer. I got the wrapper off, now I can get to the candy. Derivative of sine is cosine. I'm not touching the middle yet because I'm just eating the candy. Now the candy's gone. Now you can get to the gum in the middle. Derivative of 7x squared is, bring the 2 down, 14x. Okay, but we're not done yet because I really wanted g prime of the square root of pi over 7. Now some people freak out when they see problems like this because it's a square root and there's a pi there. It's really not that bad. Just be very careful when you write this down. It is 7 times the square root of pi over 7 squared. Be very careful when you write this. Don't write sloppily. Everywhere there's an x, I'm just putting square root, oh, a lot of parentheses here. Oh my god. Square root of pi over 7. And 14 times square root of pi over 7. Okay? Now, this gets real easy real quick because square root of pi over 7 squared is just pi over 7. So I have e to the sine of 7 times pi over 7, which you can probably see right away. The 7s are going to cancel. This is going to turn into just pi over 7. And then I still have, well, 14 times square root of pi over 7. Not much really happens there, unfortunately. But that's okay. Alright, I got to move up here. I'm running out of space. I'm going to now replace every 7 times pi over 7 with just pi, because the 7s will cancel. So e to the sine of pi times cosine of pi. Good old unit circles coming. 7. Okay, so here's pi. Whoop, right there. Ordered pair is -1, 0. So that means sine of pi, the y value is 0. So I have e to the 0 times cosine of pi is the x, it's -1, times 14 times the square root of pi over 7. E to the 0 is 1. So I'm going to put a big 1 over here. 1 times -1, I really end up with -14 times the square root of pi over 7. Okay, there's your final answer. And, sorry, I ran on to the next problem a little bit here. Let me draw a line to separate. Example 3, final one. I have my function h, and it's the square root of x times e to the 5x cubed. Oh boy, it's getting complicated now. I have a product rule and a chain rule and e action going on here. I definitely know it's the product rule because the square root of x and e are 2 separate functions, and I'm multiplying them together, so that means product. Multiplication is product. Don't forget your product rule here. We already know this. So some people like to do the derivative of the first times the second. Some people like to do first times the derivative of a second. I'm going to do the first one here. Feel free to try it this way and then compare if you'd like. Just notice that square root of x is x to the 1/2. I'm always going to think of it like that. So when I do the derivative, I have a power to bring down. So let's do the derivative of the first. So the derivative of square root of x is 1/2 times x, subtract 1 to the negative 1/2. That's the derivative of the first times second, so I'm not changing that at all, plus first times the derivative of the second. So let's do the derivative of this. So I have two layers. I have e to some function, that's my outer, and my inner, which is the gum, it's pink, is 5x cubed. Derivative of the outside is just itself, because the derivative of e to some function is e to some function, times the derivative of the inside. Now I'm ready to get to the gum in the middle. The candy's gone. Derivative of 5x cubed is, bring the 3 down, 15x squared. Okay, so this right here was the candy, and this right here was the inside gum. All right, so we're going to practice this in class tomorrow. Just realize if you wanted to clean this up a little bit, you could bring the x to the negative 1/2 in the denominator. So 2 square root of x. And then that way there's no negative exponents. That's not the end of the world either way. We'll practice simplifying more in class. But you could write it like that if you wanted. All right, I'll see you tomorrow in class, and we'll practice this.